I repeat this definition I had last time. So if I've got an algebraic set, then we write k of x. So this is the polynomial ring in the given variables divided by I of x. So I of x is all the set of all functions that vanish, polynomial functions that vanish on x. So this is the ring of polynomial functions x to k. So this is called the coordinate ring. Of x. So you can say, you know, coordinate means x1 up to xn. So these are in k of x. So you know, here's my x contained in an, and you know, so the mapping x1 to a1. This is certainly a function on x, and we're defining it to be a polynomial function. We can think of this, well, it's a linear function. It's just the coordinate x1 of each point, and so if I take the set of all of these, then they generate a ring, and I of x is just the ideal that holds between them as functions on x. So I hope the definition is clear. Anyway, as I explained last time, this ring, the ideals of this ring, the ideals of k of x correspond to algebraic subsets of x. And this is sort of IV stuff. Like the Nullstellensatz. So if you understand the Nullstellensatz for an, then you just repeat everything there, and you get, this is basically what I said in the last lecture. Okay, so now I want to use this to make maps. Say, you know, x to y, if this is an and this is an. So if I've got two different algebraic sets, I can use so this is just a definition, polynomial map. F from x to y, where x in an and y in AMK. These are just the things I've been talking about all the time are algebraic sets, algebraic subsets. Well, I mean, it's what it says. It's a polynomial map. It's a map from x to y given by p maps to f1 of p up to fm of p. And the conditions are that each fi is a polynomial function on x, and that f of p is in y. Right, so I mean, so you know, in mathematics, when you define an object, you often want also to define maps between the objects. So you define a group and you define group homomorphisms. So this is the same kind of thing. I've defined the objects X as algebraic sets. Later on, very soon, I'll be able to call them algebraic varieties. So this is literally a locus, a set of points in space defined by a number of polynomials vanishing. So that those are the objects that we want to study, and now I want to study the maps between different objects. So objects and maps between objects together forming a category. Right, so I'm trying to define what I mean by a polynomial map, and of course we already have some ideas. So you know, here for example, when I did this map T maps to, so A1 maps to you know, the curve C, y squared equals x cubed in A2. I do this by mapping T to x equals t cubed, y equals t squared, or the other way around. Well, x equals t squared, y equals t cubed. Okay, and so this is a polynomial map. Okay, and so I want to say that so there's so F is an isomorphism so this is more or less the same in every category. I've got, so F is going from x to y, and I want, there exists a G going from y to x, such that, you know, F composed with G is the identity, and G composed with F is the identity, and you only have to think about what this means. F composed with G is the map G y to x, and then followed by F x to y. So this is the identity of y, and this is the identity of x. Right, so these are just definitions. These are just standard things you'd say in any category. Right? So notice that a polynomial function on x, that means exactly that fi is in k of x. Right? So I have this ring on k of x, so almost by definition of an algebraic set, it has this ring of polynomial functions on it. And so I can use this to discuss subvarieties of x, to define, for example, a set of points in x where some polynomials vanish. That was the stuff I discussed in the last lecture. And now I'm using it to define maps between varieties. So let me sort of say I'm going to think of x1 up to xn here as being functions here, and y1 up to ym as being functions there. So in other words, so in the definition of polynomial map, in other words, a polynomial map f from x to y is a map given by so P is x1 up to xn maps to, so there'll be y1 of y1 of P, yn of P where each of these, this is f1, fn, so where the fi are certain elements in k of x. So they're polynomial functions on x. And so that means there are restrictions. So each fi, each y equals yi is fi of x1 up to xn is a polynomial. Right. So when I write down a polynomial, I have an idea that I'm writing down something in this ring, in the polynomial ring, but I'm considering it only up to the ideal of things vanishing on x. So in other words, I'm really considering it just as a function on x. Okay, so the thing we get is this theorem 4.4 of the book. That, so it says basically polynomial maps f from x to y correspond exactly to k algebra homomorphisms k of y maps back to k of x. So this is the place where you start worrying that maybe I've got things wrong, and this is sort of one of the central, maybe it's not exactly a difficulty, but so notice that it's contravariant. So phi is called f upper star, and f is called f of phi. And the f goes forwards from x to y, whereas the phi, the capital Phi, goes from y back to x. Okay, so if you just think about this in a very simple example, here's a very simple, but in some ways typical example of a polynomial map. I'm taking t, I'm taking the point t of the space, and I'm mapping him forwards to the point x and y of this space, x comma y. So what do I have to do to that? I have to say, right, I'm going to take this space has got coordinates of x and y. What I have to do is take x to some polynomial x of t, some polynomial in t, and then the same y. Right? And when I did this, I checked in advance that y squared is x cubed. So the function that I chose for y and the function that I chose to x are supposed to satisfy this equation. Right? So that's in order to guarantee that the image of the map is actually contained in C. Now this procedure I told you, choosing some polynomial in t to be the value of x and some polynomial in t to be the value of y, and arranging for those to satisfy this equation, is exactly what you need to do to make a homomorphism k of x, y to k of t. Right? So let me just sort of interrupt myself. K algebra homomorphism. So, if A and B are rings, F, then, phi. Homomorphism, you know the definition, I've already said it. It means that phi of, A plus or minus B is phi of A plus or minus phi of B, and A times B is A times phi of B. Right, but it means something else. So the rings that I'm talking about contain the given field K. Right. So if I'm working over the complex numbers, and what I want is for this map here, F, this map phi, to be the identity here. So this is just the identity map from K to K. Right. So all the maps I'm going to be talking about, the rings, all the ring homomorphisms I talk about, it isn't any old ring, it's a ring that contains the ground field. So, this is a ring of functions on a space, and it contains the constant functions to the field K. Okay, and so I want the constant functions to map to the constant functions. This is an algebraic assumption that it's a homomorph. So this is a. So this means in particular that makes A into a K vector space, and the condition here is that phi is K linear. Right. So this condition here, that it's the identity from K to K, and that this is a K linear homomorphism between vector spaces, these are the same condition. It's the same condition. Right? The copy of K that's contained in A is generated by 1. So this is K times 1A. Right? And so here I have a copy of K generated by K times 1B. Right? I'm committed to taking 1A to 1B. That's part of the definition of homomorphism. And I also want to know that I'm K linear. So if I'm K linear, then I'm certainly taking the copy of K there to the copy of K. Okay, so this is not a difficult point. I'm just saying why I say K-algebra homomorphism rather than just ring homomorphism. Okay, so to go back to this, example, right? If I want to take a map from A1 to a curve in A2, I have to choose. I have to take the point T and send him to X some function of T and Y some function of T. And I have to do it so that the equation of the curve K, the equation of the curve C is satisfied. Right? That means I can make a ring homomorphism from polynomial ring in X and Y to this by sending X into T, X into this value, T squared, Y into T cubed, and checking that the kernel here, the kernel is generated, in this case generated by this one guy, is mapped to 0. Okay, so maybe everybody in the room except me would have been happy if I'd written phi going from K of X to K of Y. Right? But that doesn't make sense. The thing that makes sense is what I wrote. Right? And you really need to think about this. So the map phi is phi upper star is composition of functions. Right, so here's my X. I'm mapping him F to Y. Right, now if I've got an element, G in K of Y, then the G is a polynomial function on X. The G is a polynomial function on Y. Right, so it's a map to K. So given this apparatus, what can I do? I can compose. Right, I can write G composed with F. So this is the functional notation. It just means G of F of X. Right, and I can think of this as being F upper star of G. In other words, I can, so this is phi of g. Okay, so look, the thing that's happening here is this structure, k of y, and the other structure, k of x here, are functions on x and y. They're not points of x and y. They're functions of x and y. So there is something sort of intrinsically contravariant, so going backwards, that's happening here. So the elements I'm talking about here in this ring are certain functions on y. They're certain polynomial functions on y. The map here, f, is a polynomial map from x to y. So if I take the composite here, what I'm doing is I'm substituting one polynomial in others, and I'm getting this. Okay, so let me explain. I've been trying to explain the statement of the theorem. In particular, this point that you really need to be aware of, that the map goes backwards. So when you write phi upper star, this means contravariant. Right, the relation between x and y here, and k of x and k of y, the maps are always going to go the other way. That's what contravariant means. Okay, so let me try and state the theorem more carefully, and so you know, I mean, it's stated carefully in the book. I don't want to just read the book; it's boring for you, and it's. So what do I say? I say two different. I put it in two different points. Well, one is given. So theorem 4.4 in more detail. Number one, it's saying that f to x to y. So this is x in an and y in am. Right, here I've got these coordinates x1 up to xn, here I've got y1 up to yn. This induces a K-algebra homomorphism from k of y, so called phi, or f upper star, and it's going, as I said, from k of y to k of x. Okay, and it's given by yi maps to fi. Okay, so this ring here is k of y1 up to ym, sorry, divided by iy. Okay, so this is a polynomial ring generated by y1 up to ym and then divided out by this ideal. So I can define a map from the polynomial ring, forget about the ideal just a moment. If I'm trying to define an ideal from the polynomial ring, what I want to know is where is each of these yi's going to. So I've told you, each of the yi's is going to fi. Right? Now, why does setting this like this and then just extending it by polynomial operations? So if I know where the generators go, I know where all the elements of the ring go, because that's just the ring operations. Right? Polynomial, everything in the ring can be obtained from by these three operations, the k vector space structure and the. Right? So why does that kill this ideal? Well, I tell you, this map here from x to the space there doesn't go to the whole space. It ends up precisely in this ideal, right? Which means that if p is in x, then f, you know, whatever it is, f1 up to fm of p is in y, right? So y is an algebraic subset. So y is defined by, so for all g in Iy, g of f1 of p, fm of p, right, is saying this map, this guy here, f1 of p up to fm of p, is the image of the point p and f in y, so this is supposed to be a point of y. So y is defined by the vanishing of these polynomials, so if I take one of these polynomials and evaluate something, I've got to get 0. Right, and that means that the thing that's written here is f upper star of g applied to p. Right, it's I take the point p here, I map it forwards into y using these functions, and then I map it into k using g. Right, so this is g, a composite function g of those guys, right? And because all of those points lie in y, this thing is 0. So in other words, the Iy, I tell you how I'm going to map the generators of the ring there, and the argument I gave said the condition that the image of the geometric map f is in y, says that I take any of these Iy's and then it maps to 0 under this. So Iy maps to 0 there. So therefore the map induces a k-algebra homomorphism from the quotient. Right, I've done exactly what I need to do to make a homomorphism from the quotient. Right, namely I take these yi's, I send the yi's somewhere, and then I arrange that all the relations that hold between the yi's map identically 0 there. So if you understood this example, then you can follow exactly what's happening here. I have to map the A1 into A2, and the t has to go somewhere, so the point of the space with coordinate t is mapped to the point there with coordinates t squared t cubed. Right? These are chosen polynomial elements in here. The map goes backwards here. The map on the composite map goes backwards. I take a polynomial in x and y, and I map him to that polynomial evaluated on t squared t cubed. Okay, so that's basically, there's nothing difficult about it except for the psychology that you're not usually used to thinking of, geometry and algebra at the same time. Okay, so second part. Conversely, a k-algebra homomorphism k-algebra homomorphism, so let me call him phi now, going from k of y to k of x, induces a map, so gives rise to a polynomial map f phi from x to y with phi equals f upper star. Okay, so I'm just saying, if you have one of these guys, if you have the polynomial over there, I said if you have the polynomial map, then you get the k-algebra homomorphism. Here I'm saying, and also the other way around. If you have the k-algebra homomorphism, then you get a polynomial map. Right? So what am I going to do here? Well, this guy here is y1 up to ym polynomial ring, and then divided out by ideal of y. So so the phi must map yi into some fi in k of x. Okay, so I'm going to choose a representative. I'm going to choose fi twiddles in k of x1 up to xn. Right. So this is k of x1 up to xn divided out by ideal of x. So basically, it's impossible to say what fi is here without saying what fi twiddles is. This is a quotient ring, so take something in the ordinary polynomial ring, right? And now let's now I consider the map an to am defined by xi mapped to fi twiddles. So I'm sorry. Have I said something sensible? Have I said something? F1 twiddles of x1 up to xn, F2 twiddles, and so on up to Fm twiddles. Okay, so so far these are just some polynomials, and so I can certainly map an to am by just choosing any polynomials there. Right, and now we have to see that the conditions I have on this are enough to guarantee that x in there maps to y in there. Right, so the point is just that this phi from k to y to kx. So this kills iy. Right? So I've got, sorry, it's just a little bit hot. So the thing I'm given in this section is a k algebra, a homomorphism of k algebras from k of y to k of x. So this guy here is generated by y1 up to ym up to some ideal iy. Right? So the capital phi there kills the ideal iy by definition. Right? And so here I'm saying, let's suppose that the yi maps to this fi twiddles. What do I want to say? I want to say that so the thing I'm doing here is I'm mapping the whole of an to the whole of am. Right? And so that map is not required is not required to satisfy anything. So I'm just taking x1 up to xn into any choice of polynomials here. Right? Now I want to know that if my point P was in x, then this image point is in y. Well, what does it mean to be in y? It means any polynomial in y here is 0 on this image. Right? And that's true because take any polynomial and take any element in I of y, and then evaluate him on this, what I'm getting is the polynomial phi evaluated on f1 up to fn, so that's 0. Right? This, if I take phi and I apply him to one of these things, so I'm saying that phi is taking y1 up to ym into something, and the iy goes to 0. Right? So the sorry, it's just a little bit hot, and I'm trying to rush the argument, so it's not very convincing. But you can easily read what's written in the textbook. So the condition that phi is defined on ky, kx1 up to y1 up to ym divided by iy is what you need, tells us that g of f1 twiddles to fm twiddles is 0 for all. Sorry, 0 on x. So for all g in iy. Right, and this means that so look, why don't I call this f here? So then it means that f upper star of iy is contained in ix. So, okay. I mean, maybe you were more convinced by the first part than the second part, and maybe you can read read what it says in the textbook. So, you know, what do we need to construct a polynomial map from x to y? The thing we need to construct is certain polynomials in x1 up to xn, called f1 of p up to fm of p. Right? So I need, in order to make this map, I've got to tell you where I'm taking x1 up to xn, and that's got to be a certain f1 up to fm. Right? And what do we need these to satisfy? We need to satisfy the condition that they define a ring homomorphism. Conversely, if I've got the ring homomorphism, then these yi's, at least lifted up to the polynomial ring, must map forward to some class of polynomials here. Right? And so the data required to make this homomorphism of algebras is exactly the same as the data over there. Okay, so in the third part, so Theorem 4.4 has part 3, which is saying that you know, if I do x to y to z, f and g, then g upper star, composition g f upper star is f upper star g upper star. Right. So the thing the book doesn't really say is that this correspondence f goes to f star is a contravariant functor. Anyway, don't worry about this. I'm just you know, when I wrote the textbook, it was in 1980, and you know, everybody had heard you know, functors and so on for about 20 years, and I didn't want to make a big fuss about it. But it is all contained there if you read it carefully. Okay, so let me sort of summarize this whole discussion. So the ring, the algebraic subset X in AN of K gives rise to a coordinate ring. K of X, which is K of x1 up to xn divided by I of x. Right. So if you know the algebraic subset in there, then you know this coordinate ring. Conversely, if you know the coordinate ring K of x plus a set of generators x1 up to xn. So to say that I know a set of generators is just the same as saying that I know how to represent this ring K of x as a polynomial ring divided out by an ideal. So this set of generators means, i.e., a representation in that form. Right, so given this, I go to Ix is the relations holding in K of x between the chosen generators x1 up to xn, right? And this is a finitely generated ideal. This is an ideal of the polynomial ring, so it's finitely generated. So and then therefore gives x in AN. Right. So knowing the algebraic subset together with its embedding into affine space is the same thing as knowing the coordinate ring together with its set of generators. I can get from one to the other and I can come back. Right? And then, you know, a map f to y is the same as you know, K of x comes from K of y. And so this is, you know, an equivalence of categories, if you want, between algebraic subsets up to polynomial maps and coordinate rings. Okay, so from now on, I'm going to use the definition of affine algebraic variety. So definition, affine algebraic variety X is a set X and then plus a ring of functions K of x on x such that if I choose generators, okay. Let me try and say it slightly in a slightly more collected way. So a ring of functions such that K of x is finitely generated over k. So let me say over k. And has no, is radical. Right, and choosing, and any choice of generators x1 up to xn of kx defines an embedding x into an of k as an algebraic subset. Okay, so look, what I'm doing here is worrying about a certain very theoretical point. And the theoretical point is that I want to be able to define an algebraic variety independently of, so without necessarily embedding it into a fixed space. So far I've been talking about an algebraic subset. In other words, I have a fixed ambient space, I have a fixed space in which everything is living, and I only want to define subsets of that space. Right? And the problem is, you know, maybe I've got two different things that are isomorphic, that are the same, but that are just embedded in space in different ways. And so I'm trying to get away from that. So this is my definition. Right? I have a set, and I have a certain ring of functions on X. And if I choose generators, x1 up to xn for the ring, then this is defining a map. So this is the point P maps to x1 at P up to xn at P. And you know this is an algebraic set. This is the ideal. So x is V of J, where J is the ideal of all relations holding between the AIs, between the XI. Okay, so the way I've stated it, I've got a set here, and I've got a ring of functions on it. And I can choose generators in any way I like. Right? And if I choose generators in some way, then there's automatically an ideal of relations holding between it. So choosing generators means making this thing equal to k of x1 up to xn divided by some ideal. Right? This ideal J is then just a set of relations that hold in this ring between this set of generators. Okay? So my definition is that I've got to have a set X and a ring of functions on it, so that if I choose the generators, I get this ideal. Then this is an embedding there into there, right? And the image is just the set X embedded by this function, and it's supposed to be an algebraic subset. Okay, so you know, you could say, well, I'm going to make one choice of generators and just stick to that, and then I get the old definition, the same as then I just get this algebraic subset. Okay, so you don't need this definition. You can forget this definition if you want to. But the point of the definition is that it allows us to make statements about X that are independent of the choice of coordinates. Okay, so let me say corollary of the main theorem, corollary of theorem 4.4. So if I've got f from x to y, then it's an isomorphism, polynomial map. F from x to y is an isomorphism if and only if phi, which is f upper star, from k of y to k of x, is an isomorphism. So, in other words, to say that the thing was an isomorphism in geometry means that I can go forwards by a map. So this is saying I've got x to y back to x like this, so that this is the identity on x. Also, y goes to x goes to y is the identity on y, but let's sort of not worry about that. Right? This is supposed to be the identity on x. So if I do the identity on x upper star, this is certainly the identity on f of the identity on k of x, right? And this is supposed to be g upper star f upper star. Okay. F upper star g upper star. I don't know. Right. So in other words, if I've got an isomorphism here, then I've got a map of rings there and a map back, which when I compose, just give me the identity on the rings. Right. So this is look. The point I'm making is that, and the point that you need to be aware of, is that an algebraic variety is not just a set. So, a set doesn't have any interesting properties. A set has cardinality and nothing more. Right? Whereas an algebraic variety has lots and lots of interesting properties. And, you can go on and do number theory or complex analysis or anything you like with it. And where's that coming from? It's coming from the fact that we know locally the polynomial maps on it. Right. So let me. What am I trying to say? So let me go back to this example. So here's A1 with coordinate t, and I'm mapping forwards to the curve C, which is y squared equals x cubed in A2. So this map is mapping to x equals t squared and y equals t cubed. So, is this map an isomorphism? Well, it would be a very strange subject if it were an isomorphism, because this one here is, the simplest thing you can have. It's certainly, all the points are equivalent. It has lots of translations and so on. There's no points here are marked out as being special. And this one here is singular at one point. Right? And so what's the difference between the two? How do you tell the two apart? So if I think of k of c, this is k of, x, y, divided out by relation y squared equals x cubed. Right? And I can take this and I can embed him into k of t. This is this map f. This is phi, which is f upper star. Right? And the map is given by, I take x into t squared, and I take y into t cubed. right? And the relation is satisfied. So, is this an isomorphism? Well, obviously not. This obviously says that this guy here is equal to k of t squared t cubed, right, contained in k of t. Right, what's the difference? Well, you need two generators here. The element little t is not in there. If you were doing differential geometry, you might write down d by dt of x and y and so on, and discover that when I do d by dt of these, I get 0. So this, there's a tangent vector there, and this tangent vector gets, mapped to a singular point. This is sort of, I'm making a big story out of a very, very simple example. Anyone can see this is not an isomorphism, right? But what's not isomorphic about it? It's certainly a one-to-one map. This is certainly a bijection, right? But what's different between the spaces? Here's A1 and here's C. There's a bijective map. I can even map backwards by taking x, y to whatever it is, y over x or y over x. Right? I mean, this is a bijection. This is, I better do y over x all 0. 0 if x and y are both 0. It's a bijection. There's nothing, in set theory, there's nothing to distinguish between the two sets of points. But obviously the geometry is quite different, and I can, just drawing the picture, you see that they're different. So what is specifically different about them? Well, I say that this one has a coordinate ring. Up to isomorphism, this coordinate ring is k of t squared t cubed, contained in k of t. This ring here needs two generators. You can't. So if I take the ideal of the point 0, 0 here, the ideal generated by x and y, the maximum ideal of 0, 0, right? That's in there, and it's generated by x and y, and you need both generators to make the ideal, right? And so this inclusion is not an equality, and so therefore this corollary says that these two things are not isomorphic. We're going to see, if we do more things, we're going to see many more of these. Okay. On the other hand, in some ways, much more trivial example. If you take some of these varieties that we've already seen. For example, I take the hyperbola. So I'm going to take the parabola y equals x squared. Right. So this is just the graph of y x squared. Right. So here I've got t, the t line. I'm mapping him forward, and I'm mapping him to x equals t and y equals t squared. Right, so the coordinate ring here I've just got k of t. The coordinate ring here I've got k of x and y, and then I'm divided out by y squared equals y equals x squared. Right, and the map going back, the homomorphism there is taking x maps to t and y maps to t squared. Right, and so it satisfies the relation. This is a perfectly good homomorphism, but this is an isomorphism. Right, so from this point of view, as according to this definition of variety, the two constructions here, the A1 with its parameter t and this parabola with its coordinates x and y, they're isomorphic varieties. There's a correspondence here between them which makes the functions on this one exactly the same as the functions on this one. So, geometrically, in any kind of geometry, these two things are quite different objects, but nevertheless they're isomorphic. And for lots of purposes, we want to talk about varieties up to isomorphism. Okay. So, maybe I give you a brief summary of what we're going to do. So, or maybe I start, let me just start mentioning the next topic. So, the next topic is rational function field. So the point is this, that if X is now an irreducible affine variety over K, so that means he's an affine algebraic variety, as I said here, and also when I embed him like that, he's irreducible. Let me algebraic. Let me just include it. Right, then K of X, his coordinate ring, is an integral domain. Okay, so what's an integral domain good for? An integral domain is useful because I can do K of X and I can include him in a field of fractions. So this is f frac of K of X. Right, so this is a set of f over G. Right, the field of fractions. So, I want fg in K of X. G not equal to 0. What else? And then modulo this relation that's f. I mean, you know very well what I mean. Fg prime twiddles equals f prime g. Okay, so if I've got an integral domain, then I can include him in a field of fractions. This is just I allow you to make fractions of these things. And you're not allowed to have g equals 0, but on the other hand, because this was an integral domain, the only, there's no kind of ambiguity about when two such expressions are equal. Right, you know how to add them and multiply them because these are rules that you learned in primary school. So this is called the function field. Function field of X. And we've already seen examples of using this. So e.g., if I was thinking of projective space Pn is this x naught up to xn. So here I had affine space an, and I had x1 up to xn with x naught set equal 1. Right, but then if I had some other affine piece, an, for example, this was, let's say, 0. If I have an1 with x1 set equal to 0, I'm sorry, maybe I have y0, y2 up to yn. Then, these yi's, the y0 is 1 over x0, x1, and so on. So in other words, we're quite used to seeing formulas in which we take things like 1 over x1. So another example is already on the board. So I said, right, I map this forward by t squared and t cubed, right? And then when I do the map backwards, I'm writing y over x. So what is y over x? Well, you know, y over x is, I take the field of k, this is the, this is the coordinate ring of C, and then I take its field of fractions, k of x, and that includes things like this y over x. Right? So this map going backwards here is not a polynomial map, as I had before, and that's part of the reason this is not an isomorphism. This is not a polynomial map going back, it's a rational map. It's really the map of space to two-dimensional space to one-dimensional space given by y over x. Okay, so you know, many of the constructions we have seen already, and some of the constructions we'll see in the future, are not really to do with these with the coordinate ring. They're really to do with rational functions. So you know, so you know, we just established that there's this nice category of affine varieties with their coordinate rings. Why do we need to go on to function fields? Well, you'll get to the point eventually. This is so you know, this is a slightly tricky notion. So an element here. So if I take an element, let's take h in k of x, is a partially defined function on x. So namely, h, by construction, he's of the form f over g, with f and g in k of x. Right, so just like that guy, x over y, y over x over there. And so, you know, if you see y over x, then you're perfectly happy. It's a perfectly good regular function as long as the denominator is not 0. So this is a regular function. Regular, and this is a definition, this is a regular function where g is not equal to 0. Right? I'm going to come back and make that slightly more precise in a while. Right? So I've got a variety. I've got an affine variety of the type I defined over there. I'm assuming in addition that it's irreducible. Right? So you remember earlier in today's lecture I made a whole song and dance. I made a whole fuss about irreducible. Right? Irreducible means that non-empty open set is automatically dense, or it means that the set of points where two functions disagree. Anyway. So on this I'm going to write down things like, I'm going to write down rational functions. Right? And I'm going to say that, it's okay, so regular means this. So there's the domain of definition of H. So this is the set of points where H is regular. So in other words, so this is an open set in the Zariski topology. Okay, so let me come back to this at the start of next time and say it a little bit more precisely, because you know, this expression H is equal to f over g. The f over g, when you write for fractions like this, the f over g, the f and the g are not themselves uniquely determined. They're only determined up to an equivalence relation. So it will sometimes happen that f over g, that the same one and the same function h has two quite different expressions f over g. And then you have to say this regular and this domain of definition slightly more precisely. But anyway, this is the key, one of the key points in algebraic geometry, where algebraic geometry starts getting interesting and also starts getting difficult. Is where you have these rational functions. Okay, let me. I always mean to stop early and never quite succeed. Yeah, I'm sorry. So look, zero divisors. Yeah, so if I've got a ring A, zero divisor means, for example, I have x times y equals 0. Right? There's something worse than zero divisors, which is called nilpotent. When I've got a single element x and x squared equals 0. Right? And so, you know, I had this thing about the radical of an ideal. Radical of I. So this is the set of f such that f to the r is in I, f to the n is in I for some n. Right? A ring is, we say an ideal is radical if I is radical if I is equal to its own radical. In other words, if f to the n is in I implies that f is in I. Right? And so a ring A is radical. If rad of 0 equals 0, or if there don't exist any non-trivial, non-zero nilpotents. Right. So the rings that I'm talking about, the coordinate rings of my algebraic variety is kx, and they're always of the form k of little x1 up to little xn, and then divided out by I, where this ideal is radical. Right? This is, by the Nullstellensatz, this is Ix. Right? So it satisfies this radical condition. So actually, I don't need this because it's at the end the x is isomorphic to an algebraic variety. So, but it's. So any other questions? I'm happy to discuss things with people if you need it.